All right, so now we're going to go over briefly the energy of a simple harmonic oscillator. So basically, what we see here is U equals 1/2 kx squared, and kinetic energy is given by 1/2 mv squared. So we've established before that U is 1/2 kx squared when we were talking about springs way back when. And then kinetic energy is always just 1/2 mv squared. So when we talk about a simple harmonic oscillator, we see this red curve where the energy goes up quadratically as the parabola until it hits the value of 1/2 Ka squared, because that's its turnaround point. That's the maximum value of x that you get from a harmonic oscillator, as we were talking about uh, earlier when we were talking about sine and cosine waves. The maximum value that you can get is just the amplitude of the wave. So it goes up to a value of 1/2 Ka squared, whereas the kinetic energy peaks when there's no peaks when there is no displacement, and goes down the farther out you get to display, the farther displaced you get. And then the total energy equals U plus K is equal to 1/2 Ka squared cosine squared omega t plus phi, which is just 1/2 kx squared, plus m times omega squared a squared sine squared omega t plus phi, which is 1/2 mv squared. We decompose the omega squared to k over m, and that's going to give us 1/2 Ka squared times cosine squared omega t plus phi plus sine squared omega t plus phi, which is just 1/2 Ka squared. So this is just proving that uh yeah, this is just proving that the total energy is equal to 1/2 Ka squared, which is also, if you were taking a non-calculus course, a non-calculus physics course, I think this is generally how they derive the formula for the kinetic or the potential energy of the spring, generally just by knowing that it has to be constant, has to equal 1/2 Ka squared as you uh, go along the x-axis. It's going to be constant when you talk about the u and the k at the same time. So let's just save this and talk a little bit about uh, sorry, a little bit about stable versus unstable equilibriums. So an equilibrium occurs when f of x naught, where x naught is whatever x value you're centered around. It can be any value as long as f of x naught. Okay, this is getting annoying. Is equal to 0, which means that there's no force involved, which means that du dx is equal to 0. And then you can have stable or unstable equilibriums, where a stable equilibrium would look like our U here, where you have potential energy U versus X. Okay, this is getting really annoying. I keep hitting the select button. instead of the draw button. So u versus x is built up like this, where d squared u dx squared is negative. Unstable equilibrium is built like this, where there's still let's just label these unstable, where d squared u dx squared equals positive. So d squared u dx squared equals negative means that df dx is going to be, oh yeah, I got these mixed up. Sorry, that's very silly. D squared u equals positive, obviously. D squared uh u dx squared equals negative for the unstable one because it's curving down like this. So df dx has to be negative for d squared dx squared to be positive, and df dx dx has to be positive in order for it to be an unstable equilibrium. So what this means is that for df dx equals negative, if you have a force, if you push it out a little bit, then it's going to come back to its initial position. If you push it out a little bit, it comes back to its initial position. But this force, if you push it out a little bit, it keeps going out. And if you press it out a little bit, it goes out on both sides. And then you also have the saddleback potential, where it looks like this, where d squared u dx squared equals 0, which means that df dx uh doesn't, it depends on whether so whether or not it goes to the left or the right is going to determine whether it's in an unstable equal or it's pushed back, or whether it's going to be pushed to the side. So what this is interesting and all, but why was I saying earlier that uh every uh potential, every stable potential can be estimated as a simple harmonic oscillator? Well, if you remember Taylor series, it might be something that you're learning right now in your calc class. If not, you don't have to worry too much about this. It's very useful, and it's one of the things that if you get into physics, higher level physics, then basically everything's a Taylor series or a Fourier series. But Taylor series states that u of x is equal to u of x naught plus du dx x minus x naught plus 1/2 d squared u dx squared x minus x naught squared plus 1/3 times 2 d squared u or d cubed u dx cubed x minus x naught cubed plus dot dot dot, where it's just however far out you are placed from however you have some initial position, and then you have a series which is dependent on the distance from that initial position, x minus x naught. Uh, to higher degrees, the farther out you go. So if you have a small x minus x naught, then you're going to worry mostly about the x minus x naught or x minus x naught squared term. But as you get bigger, you have to worry about the x minus x naught cubed or the x minus x naught to the fourth, because those get bigger. The bigger, those aren't very, as x minus x naught is less than 1, then that's going to, those are going to be smaller than x minus x naught. But if x minus x naught is greater than 1, then that's going to be bigger than x minus x, or x minus x naught squared. So the bigger terms matter. Terms disappear with small x minus x naught. So if we have this equation, and then we have equals u of x naught plus 0 times x minus x naught for any stable equilibrium, plus 1/2 d squared u, or let's put this on the next line even though it's getting kind of cramped, plus 1/2 d squared u dx squared times x minus x naught squared. Then this basically becomes u of x equals u naught plus some factor 1/2 d squared u dx squared x minus x naught squared, which is basically the spring potential energy. So up to a certain point, up to a certain value of u, or a value of x minus x naught, this becomes the spring potential. This becomes the spring potential energy and moves like a spring. So up until you get to higher values of displacement, every stable equilibrium is going to act like a spring, restoring itself to its initial position and going back and forth like a sine wave. So that's the main thing that I want to get across here. I'm going to have one last section about damped harmonic motion, and then I'm going to let you go for Thanksgiving.